In section 13, we're talking about the preparation and reaction of nitriles. Now remember, a carboxylic acid is a molecule that has 3 total bonds to 3 total carbon-oxygen bonds, okay? 2 to the oxygen on top, 1 to the oxygen on the right, so 3 total CO bonds, or whatever you want to call it, okay? Now a nitrile, remember, has this arrangement, bonding arrangement, okay? And you might think, whoa, that's just completely different. That does not look like a carboxylic acid derivative. But this has 3 carbon-nitrogen bonds total. So it's kind of in the same oxidation state, and it can easily be converted to carboxylic acids and derivatives and vice versa. So we want to consider its reaction now. Now, we did see previously one way to make nitriles, and that was an SN2 reaction with cyanide. Okay, cyanide. So if you have a primary or a secondary alkyl halide, and you treat this with sodium cyanide, some polar aprotic solvent, but we won't get into that, you can form a nitrile. We can also draw it with the carbon-nitrogen triple bond shown. Now, the thing to remember here is that you've introduced a new carbon. So that right there is a carbon-carbon bond that we've just created, okay? Keep in mind that this works for secondary or tertiary alkyl halides, okay? This guy here is secondary because it's bonded to 2 additional carbon atoms, okay? And we've talked about that before, so I won't go into it in greater detail now. The second way to create nitriles is with a dehydrating reagent. Specifically primary amides, okay? So if we have an amide, and we were to treat this with something that removed water, well, I'll draw it over here. You know, we want to remove this oxygen and these 2 hydrogens, right? So that's basically removing water from this chemical reaction. But the water has an interesting way of reacting with thionyl chloride, and so you do indeed form the, you know, the nitrile here. Okay. In addition to that, you form sulfur dioxide and 2 equivalents of hydrogen chloride. Okay. Now the mechanism's in the book, but I'm not going to go over it because I don't require my class to memorize it, but the mechanism is in the book if you want to read it. It's interesting and all, but it doesn't really follow the pattern of nucleophilic acyl substitution. It's just very weird. But anyways, it's in there. It's quite short, actually. So that's a useful mechanism to form nitriles. So think about that. You know, how do you go from something like this to something like this? Well, you just want to substitute the bromine for the cyanide, so you can just add sodium cyanide. Well, that's easy. How do you go from something like this to something like this? Okay, so here we have a carbon, and whoops, I messed that up. Pardon me. And here we go to the same kind of thing, okay? And I'll highlight the carbon in green there, okay? So there's no change in carbon. We know we're not adding sodium cyanide. That would give you 1 additional carbon. So somehow that C is changing to that. Well, one way that you can do this is to add ammonia to this, right? Excess ammonia. Excess ammonia would give you the amide. And then the last way to do this would be to add thionyl chloride. Okay? So that 2 is a little sloppy, SOCO2. Okay? And that's a 2-step sequence there, okay? We've seen thionyl chloride before, but that was for a, a side reaction, a different reaction. So on the side here, I'll show you what we normally use thionyl chloride for. Thionyl chloride is for creating acid chlorides. Okay, so don't confuse these. Okay, that's one use of thionyl chloride. This is another use of thionyl chloride. All right, so that's the second way nitriles can be made. You use SOCl2. All right, it just depends on what you're starting with, okay? If you're starting with a carboxylic acid or an amide or something like that, this might be the way. If you're starting with just a simple alkyl halide, this might be the way. All right? So let me now discuss, I think I'm on reaction 3 for this chapter, the hydrolysis of nitriles. Okay? And you basically have 2 ways, okay? We'll call this method A. If you have a nitrile, and you react this with H3O plus and heat, and we're talking lots and lots and lots of heat, you will form a carboxylic acid and ammonium. Okay, I'll take you through the mechanism for this. All right, so this is acid catalyzed hydrolysis or acid hydrolysis. All right, aqueous acid. The other way of doing this is to treat this with base. Now this is a 2-step sequence. So you first want to add sodium hydroxide, which is aqueous. Then you want to add acid at the end of this, okay? And this will make your carboxylic acid. Okay? And we're leaving the nitrogen out here, but let me go ahead and show you how this reaction occurs. Okay. So for the acid-catalyzed hydrolysis, let's take propane nitrile. And let's make a propanoic acid and ammonium. Okay. So once again, a tidbit for memorizing this is that acids, right, are going to make the acid form here, and ammonium is a weak acid. So how do we do this reaction mechanism? Well, the first step is always, if you have acid present in your reaction, is to protonate. Okay, so we're going to protonate the nitrogen. Remember, the nitrogen of a nitrile contains a lone pair on the nitrogen. So we protonate like that. Now we want to use water to attack. Okay. And let's label these steps. So we have protonation, and then attack. So the triple bond now becomes a double bond. And we've got to draw the two hydrogens on that oxygen that come in from the water. And so what you'll want to do now are a number of different deprotonations and protonations, things like that. So what we want to do now is we want to deprotonate. So that step is labeled D here. So there's the pad part of it. Now I just want to point out that this looks a lot like an imine. Okay, when you have an imine, you can add acid and water, lots of water, to form, a C double bond O, or a ketone. And ammonia is going to be in the acidic form ammonium. Okay, so at this point we want to do basically an imine hydrolysis. So if you didn't really learn imine hydrolysis well, now's your chance to kind of refresh your memory. So what we want to do is protonate. You see, we got to kick off the nitrogen, right? So we need to protonate it and get it into a suitable leaving group. So what we want to do is protonate the nitrogen. Okay, so we're going to lose these lone pairs here and attack. Okay, attack H+. All right, now we have, once again, an electrophile, right? So we want to use water to attack this. So we attack the carbonyl. Electrons go up to their nitrogen. So let's label these steps again. So this is protonation. We had attack. All right. And so we have, once again, this tetrahedral intermediate. Now we'll take water, and we've got to do a bunch of protonation deprotonations. Remember, again, we want to kick off the nitrogen. Neutral leaving groups are going to be better when you're dealing with nitrogen and oxygen. So we deprotonate, and the intermediate there we get is going to be this guy here, okay? And so now we want to protonate the nitrogen. And we've situated ourselves to kick off ammonia. So here we have the ammonium guy, okay? It's a better leaving group. So we'll take lone pairs. Either of these two oxygens would be fine. I'll take this one here, and I will create a carbon-oxygen pi bond, and I'll break the carbon-nitrogen bond. And that will be your elimination step. Okay. And that makes your carboxylic acid. And you know, you form your ammonia, right? We discussed what happens with the ammonia. The ammonia gets protonated. That goes on to form ammonium, which we don't really worry about. What we worry about mostly is the fate of this carboxylic acid. And remember that if you have water present, that can do a lot of protonating and deprotonating. So you want to deprotonate that to give you the product. We'll label that in green here, okay? So let's review our steps here with purple, I guess. We have protonation, then attack, and then deprotonation, okay? And that gets you to here. And then you have amine hydrolysis, which is PADPED, okay? So that's PADPED. So a lot of students really become overwhelmed, but the new steps are PAD. The first three steps are new. The last steps are all the same as what we saw before. So you have PADPED, P-A-D-P-E-D. So if we spell our sentence out or whatever, it'd be PADPED. Okay? So this whole mechanism is protonation, attack, deprotonation, protonation, attack, deprotonation, protonation, eliminate, deprotonation. So quite lengthy. Probably this won't be on your exam for your class because it's just so, lengthy. But I wanted to be complete and have it here on this video. What about base-catalyzed reactions? So base hydrolysis of nitriles. This is significantly shorter, and it could very well be on your exam. So again, we'll use the same propane nitrile, and we'll treat this with sodium hydroxide, H2O, and what you get here is the I'll show it as a two-step thing here. So what you form here is a amide, okay? And then in step 2, you'd have to do H3O plus and heat. Okay, so it's kind of like busy, because if you took your nitrile, I'll draw the products here, sorry. If you took your nitrile and you treated it with H3O plus and heat, it'd just be one step. It would just take one step, and you would come back the next day and you'd have your products. So this is just a two-step thing. So, I've showed you this mechanism before. So let me just focus on this yellow highlighted box here. I'm going to show you how the nitrile gets converted to amides, okay? And this is a mechanism that's in your book. It's mechanism 21.15, all right? So a nitrile, if we treated this with aqueous hydroxide, right? So we have hydroxide present. There's water as a solvent or a co-solvent. What you'll form here is your primary amide. And let me just highlight the atoms here. We have an oxygen, and we have two hydrogens. That's basically water, okay? I know we're calling this a hydrolysis. We're not really breaking anything apart in this molecule. I like to think more of it as an addition reaction, but I'm going to call it base hydrolysis. So what you want to do is grab your hydroxide, attack the carbon of the nitrile, and this structure up here looks kind of weird, but I mean, if you follow the curved arrows, nitrogen with only 2 bonds is going to have a formal charge of -1, okay? And you form this kind of intermediate. Now what you want to do is immediately protonate, okay? And there's several different ways you could draw this mechanism, but anyways, I'll just show you exactly what's in the book so we're not all confused a little bit. Now, what you want to do now is deprotonate, right? So this kind of looks like a carboxylic acid. It's acidic. What do we have in solution? We have hydroxide, okay? So here's where you would want to use hydroxide, not water, okay? So use hydroxide to deprotonate this. And I'll show this in two separate kind of steps. What you form is this guy here. Okay. And it's key to recognize that there's a resonance structure you can draw for this. Okay, we can draw the negative charge on the oxygen or on the nitrogen. So remember, nitrogen with two bonds is going to have a formal charge of -1. I dropped a carbon off my molecule there. Okay, so now we can protonate. And so you want to protonate by pulling off a proton from water. You don't want to draw H+, because look at the reaction mechanism conditions. It's hydroxide, so don't use H+. So here's where you want to protonate. And then we're going to draw two hydrogens now on this guy here. So that's where we stop. Under basic condition, we kind of just stop there, okay? So what do we have? We have attack, then protonate, then deprotonate, and then protonate. So it doesn't make a nice phrase that could be pronounced. We have APDP, all right? APDP. And then I don't know, remember what the letters are for that. I don't memorize it, but there's a bunch of steps for that, okay? So anyways, the key to this point is that nitriles can react. Nucleophiles attack this carbon, which is delta plus, and electrons move to the nitrogen, which is delta minus, okay? Now here's where we want to pay very close attention to things and what's happening. Nitriles can react with Grignard reagents. And the reaction here is going to look something like this. So if we have a nitrile, we'll draw out the bond this time. And you want to add a, let's do methyl magnesium bromide, followed by acid. Normally after a Grignard you use H2O, but here we want to use H3O plus because we're going to hydrolyze the I'll draw the methyl group in purple. So there's my CH3. So you make ketones, okay? So nitriles make ketones. Very strange, right? So let me just sketch out how this works. There's no mechanism shown in your book. So let me just sketch out how this works. Remember that whenever you have a Grignard, you have a carbon with only 3 bonds and a negative charge. Okay, and that's going to be a nucleophile to attack, once again, the carbon, and electrons move to the nitrogen. Okay, and what you get here is this guy here. Okay, and this just stays there and doesn't do anything, okay? Until you come along in step 2 and you add acid. And I just want to, at this point, just sketch out what happens here. You know, when you add acid, you form an imine. So this is protonation. Okay? And then what you do is you hydrolyze the imine. Okay? Which was PAD or whatever, those bunch of mechanisms, okay? So that will get you to the point where you have a ketone, okay? And where does that nitrogen go? You lose ammonium, okay? You lose ammonium ion in acid conditions. So the first step, you should be very comfortable showing where that Grignard attacks, and then just kind of conceptually understand, well, the nitrogen goes away because instead of a carbon-nitrogen double bond, you form a carbon-oxygen double bond when you hydrolyze it, okay? You add excess water there, okay? So let's look at the last reaction. So this is reaction 4. Reaction 5, we've talked about that in the very beginning, but basically you can reduce, we talked about this, I don't know when, but you can take nitriles and you can treat this with excess lithium aluminum hydride, add water, and that forms a primary amine. Okay, so I'll by the way, this is similar to the situation we saw earlier, where if you have an amide, okay, and remember these are just ditto marks, same exact conditions, the same one, the same two, you will get a primary amine where you have, you know, your 2 hydrogens there, okay? So how does this work? Let me sketch the mechanism once again for how this works. So if we have a nitrile, I always draw H- for the nucleophile present in lithium aluminum hydride. What happens is you have attack, all right? And you form something that looks like that. Okay. This is negatively charged and things like that, but you can think about this as an aldehyde, right? Aldehydes react with hydride to give you alcohols because hydride attacks the carbon, right? So this goes on to react further, right? A second hydride is going to attack this eventually to give you an amine where you've added your 2 hydrogen atoms, okay? So don't worry about the mechanism here, okay? It's not in the book and it's not in my class, at least, all right? The key reaction mechanisms you might want to look over are acid-catalyzed hydrolysis, base-hydrolyzed hydrolysis of amides. Let's do some practice problems here and for comprehension. In problem 29, we're simply interested with drawing the products. In question A here, just recall that that is a carbon, okay? And remember that this gets converted to NH2. We call this a primary amine. So here's my carbon, and then draw NH2 off of that. Okay. In B, there's a lot of stuff going on, but you remember this is a primary alkyl halide, so here's cyanide, right? Cyanide is going to attack and kick off the bromine. So let's draw this as an intermediate here. Okay, so you form this intermediate, and then what do? We add methyl magne. I meant to draw CN there. CN. Okay. So remember again, in green here, here's the carbon. Okay. And so when this reacts with Grignard, remember that the methyl group is going to attack this carbon, and electrons from the bond there are going to move to the nitrogen. So what you get after all of this acid hydrolysis of the intermediate amine, I can't say that clearly enough, you form, okay, so here's our new carbon, okay, so that carbon there was added with the cyanide, and then you have, we're making a ketone, remember, and then you have a methyl group attached to that, okay, so there's your methyl group. So that's a tricky one. There's many steps, okay? So remember again, when you add ethyl, Grignard, and acid, these first 2 steps here are going to make your ketone. So what we want to draw is, I like to sketch things out. Here's my carbon, and then I'm adding an ethyl group. Okay, so there's my ketone. Now I'm adding lithium, aluminum hydride, and water. Remember, that makes alcohols. Okay, so from the end, we're going to make, an alcohol with the ethyl group there still intact. Okay. Next, what we want to do is think carefully about what's going on here. So H3O plus heat, remember that makes carboxylic acids. So that's going to make, okay, so be careful. In green, we have a carbon, so make sure you have the carbon, and that's just going to make the carboxylic acid. So I'll be lazy and just write CO2H, okay? Here we are with problem 30. Now, in this case, the synthesis might be a little bit more difficult, and there might be more than one answer. So this is starting to get into section 14 of the book, which is synthesis strategies, okay? So we want to think about the carbon count here. We have the same number of carbons in the starting material and the product. So we just want to think about functional group manipulations, okay? How can you make, nitriles? Nitriles can come from alkyl halides. Well, we can't do that because this is not primary or secondary. They can come from primary amides, and primary amides can come from, acid chlorides. This was an example problem I illustrated before in my lecture. So what we want to do is step 1, add excess NH3. That's going to take me from an acid chloride to the amide, okay? So that's fairly straightforward. And then remember, to go from an amide to a nitrile, we need to use a dehydrating agent called thionyl chloride. Okay. In this part of the synthesis, for part B, we want to add a new carbon. There are two ways that you can add a simple carbon. One is with CO2 and Grignards. The other way is with cyanide. So I'll show you method 1. Okay. You can take the bromide, treat it with sodium cyanide. This performs the SN2 reaction to give you the nitrile, and there's an extra carbon in there now. And then if we treat this with water and acid, don't worry too much about how you write this down. You can write H2O above, H plus below, H3O plus, whatever. We get the idea. You're going to form the carboxylic acid with one additional carbon. Okay. Method 2 goes back to chapter, very beginning of chapter 21. You can take alkyl halides, you can convert them to Grignards by adding magnesium. We do this in diethyl ether. And then if you have the diethyl ether, you can if you have the Grignard, you can treat this with carbon dioxide, followed by, acid, and this will give you the carboxylic acid as well. So either way would work. We only need one answer if you're doing this on your homework, okay? So that's it for section 13. There are a lot of other practice problems in the back of the book, but that's it for just the brief introduction. Thanks for watching.